All right, so get this. We're diving deep into deep learning, image classification specifically. Ambitious, right?
It is, but the cool thing is, you don't need Google-level resources to get amazing results these days.
That's reassuring to hear. And we're working with an excerpt from Deep Learning with PyTorch Step-by-Step, right? Transfer learning is the name of the game.
Exactly. We're about to unlock some seriously cool image recognition secrets. It's all about pre-trained models.
Sounds a bit like magic to me.
Well, it kind of is, but the approachable kind. We're going to explore how these models, AlexNet, ResNet, Inception, how they can be used even if you don't have years to train a model on your own.
Those names ring a bell vaguely. Aren't those the big players, like in self-driving cars and all that?
You got it. These models cut their teeth on data sets like ImageNet, millions of images, thousands of categories. Imagine the time and computing power.
Yeah, my laptop will probably melt just thinking about it. So how does this transfer learning magic even work?
Think of it like this. Instead of baking a cake from scratch, you start with one that's already baked. Pre-trained model, your base. You just add the frosting, the decorations, fine-tune it.
So I'm not stuck kneading dough for hours. I can just get creative with the fun part. I like that. But picking the right cake, that's got to be important, right? Choosing the right pre-trained model, I mean.
Absolutely. That's where AlexNet, Inception, ResNet, they're like our cake recipes. Each has its own strengths and weaknesses.
Is there like a cheat sheet for this? This sounds way more complex than my baking skills.
The chapter actually provides a table comparing their size, speed, accuracy. Helps you pick the best for your project. No need to reinvent the wheel.
Oh, thank goodness for that. Okay, so what's the actual process here? Do we just yell transfer and hope for the best?
It's a bit more involved, thankfully. The chapter breaks it down. First, load your pre-trained model. Then, swap out the last layer, replace it with one tailored to your categories.
Hold on, let me get this straight. So if I want to classify like different bird species, I grab a pre-trained model, say AlexNet, and swap out its last layer with one that's all about robins and sparrows and ostriches.
Exactly. The pre-trained model, it already knows how to extract features from images, edges, shapes, textures. You're just teaching it to recognize your specific birds using that knowledge.
So it's like the model already knows how to see generally, and we're just focusing its vision on what we care about.
Exactly. And speaking of seeing, the chapter gets into how we can actually visualize how these models perceive the world.
Now that's getting to the mind of a machine. Tell me more.
By analyzing the features the model extracts, we can get a glimpse into its brain, so to speak.
Whoa, that's wild. Okay, but the chapter mentions some pretty complex stuff, like one-by-one convolutions and Inception modules.
Yeah, those sound a bit intimidating, I know.
Yeah.
But they're really insightful once you grasp the core idea.
Okay, because one-by-one convolutions, that seems kind of strange. Like, how can you even have a convolution with a kernel that's just one pixel?
Right. It's not about looking at neighboring pixels like traditional convolutions. It's more about finding the best way to combine color channels.
Okay, I think I'm following so far, but how does that actually work?
So these single pixels, they hold the key to simplifying things. It's like we're mixing the channels together to create a more efficient language for the model.
Yeah, it's like instead of having this massive dictionary, we're creating a more concise vocabulary that still captures the essence of the image.
So it's all about efficiency, making the model's job easier without sacrificing accuracy.
Exactly. And that brings us to those Inception modules. Remember how I said they're all about going deeper?
Yeah, but in a smart way, right? Not just stacking layers like pancakes.
Right, because that can lead to problems. Vanishing gradients, for one. Inception modules, they use these parallel branches with different kernel sizes.
So it's like looking at the same image from different angles at the same time.
You got it. Each branch, it captures features at a different scale, giving the model a more complete understanding. And guess what? Those one-by-one convolutions we talked about, they're back. I knew those tiny kernels were up to something important.
Exactly. They play a crucial role inside those Inception modules, too, managing the flow of information, helping to prevent those vanishing gradients.
It's like a perfectly choreographed dance of deep learning techniques. So much more elegant than my initial yell transfer idea. Okay, what else? We touched on batch normalization earlier.
Ah, yes. Batch normalization, another essential tool.
It sounds kind of scary, but you said it's straightforward.
It is, really. Think of it like this. You have a choir, right?
Yeah, I'm picturing a choir.
And everyone's singing at different volumes, different keys. It'd be a mess, wouldn't it?
Yeah, more like a flock of geese than a choir.
Exactly. Batch normalization is like bringing in a conductor. Make
Yeah.
sure everyone's in sync, harmonizing.
So it's bringing order to the chaos, but how does it actually work in the context of, neural networks and all that?
Well, it's all about normalizing the activations within each layer. Zero mean unit variance. It standardizes the data flowing through the network.
Keeps things flowing smoothly, prevents any information bottlenecks.
Exactly. But here's something even more interesting. Batch normalization, it can also act like a regularizer.
Oh, that dropout. But how does that work?
It adds a bit of randomness to the training, which helps prevent overfitting, like adding a pinch of salt to a recipe.
So batch normalization is like the multi-talented member of our deep learning band. Organizer, chaos tamer, and even a bit of a stylist to prevent overfitting.
I like that analogy. And speaking of talented,
Mm.
we can't forget residual connections. Those are game changers.
Right, those shortcuts in the network. But skipping over layers, it still feels a bit weird, like, aren't we missing something important?
Not at all. It's more like sometimes taking the scenic route isn't the most efficient. These shortcuts, they help the network learn what's called the identity function.
Identity function. Okay, now you're just throwing big words around.
It sounds fancy, but it's basically giving the network the option to say, hey, this information is already good as is, let's just pass it along. Especially in those super deep architectures, it prevents things getting lost.
So it's like giving our model a shortcut to bypass any unnecessary processing. Smart. And these shortcuts, they help with those vanishing gradients too, right?
Exactly. Think of it like instead of shouting across a crowded room, you have a direct line to whisper a message. That signal gets through much clearer.
So these residual blocks, if I'm picturing this right, they're like where all these concepts combine, right? Convolutions, batch normalization, and those skip connections.
Exactly. And the chapter actually shows this in action with the rock, paper, scissors data set. They used a ResNet model, put it to the test.
Oh yeah, the classic game. So how did ResNet do? Did it manage to master rock, paper, scissors?
It did pretty darn well. Even with a fairly small data set, the combination of transfer learning and that ResNet architecture, they got some seriously good accuracy on classifying those hand gestures.
That's seriously impressive. And it really drives home the point that you don't need those massive data sets to do some really cool stuff with this. We've covered a lot of ground in this deep dive. We've gone from like the basics of transfer learning all the way to peeking under the hood of these sophisticated models. We even got a little hands-on with the code too.
It's a lot to unpack, but the beauty of it is you don't have to start from scratch. There's this incredible body of work already out there, these powerful models just waiting for you to use them.
It's like we've been given this amazing toolkit, and now it's up to us to go out and build something amazing with it. Who knows what we'll create, right?
Exactly. The possibilities with image recognition and deep learning in general, they're practically limitless.
Now that is an exciting thought to end on. You've been on the deep dive, and as always, happy exploring.